So we're very pleased to have Beate Heinemann here. She's visiting from UC Berkeley, where she's a professor, and also from CERN, where she spends a lot of time. She's the deputy spokesperson for the ATLAS experiment, sitting right to the left or right of our spokesperson. And we're very happy that she's taken some time out of her very busy schedule to come talk to us about ATLAS and the LHC and what we hope for the future. So thanks.
Okay, thank you very much.
And I will turn off the lights.
Ah, yes. Thanks very much for this nice introduction and for inviting me in the first place. I was enjoy very much being in Manhattan in general, but also it was actually when I joined the LHC in 2007, one of the first things I did, I visited here because I discussed with Beate Heinemann how we could ensure that we are recording the quality of the data correctly so that we are then able to do physics analysis. So that was the last time I was here, actually. So where is the laser? Here we go. Okay. So this shows, I'll talk to you about what we've done at the LHC in the first 3 years of its running and about the next 2 decades. This shows this iconic picture of the ATLAS experiment taken in 2005 when we just had the toroidal magnet installed. And this shows the latest piece of the ATLAS detector we have just finished assembling and have not actually yet inserted into the experiment 2014, which is a new inner layer of pixel detector. This shows you at the same time the largest detector at ATLAS, the muon spectrometer, and the smallest one, the IBL, which has a diameter, a radius of only 3.9 centimeters. Okay, so this is the outline of my talk. I'll give a brief introduction, and I'll talk to you then about the Run 1 physics results and what we've learned from them, and then I'll talk about the future plans before I conclude. So what did we, or do we hope to find at the LHC? We have this standard model where we have 3 generations of quarks and leptons, and these make up the matter in the universe. And then we have force carriers, the WZ, photon, and the gluon that mediate the forces between those particles. And then within the standard model, there was predicted another particle, the Higgs boson, which has a spin 0 as opposed to spin 1 or spin 1/2. The only particle with spin 0, which breaks the electroweak symmetry and gives masses to all the fermions and the massive bosons. So this is one of the big questions. This particle had not been observed before the start of the LHC, and so one of the big questions was, why do particles have mass? And the answer was hypothesized because of the Higgs boson. Another big question is why gravity is so much weaker than the other forces, and there are possible answers to those questions related to supersymmetric particles or extra spatial dimensions. And another big question that we have today is what is dark matter? We know from cosmology, astrophysics experiments, that we know that there is a lot more dark matter in the universe than visible matter, and we have not yet been successful in associating that with a fundamental particle. And there are possible answers that we have at colliders, for instance, supersymmetric particles. And of course, there is also, which would be the greatest pleasure maybe as an experimentalist, to find something completely unexpected, a new phenomenon.
Question. I mean,
yes.
The dark energy on the right,
yes,
sort of stares at everybody.
Right.
But you don't have any.
That is,
on the left.
yes. Well, so
what is kind of the psychology that leaves it out on the left?
Yeah. So it is true that dark energy is actually an even bigger puzzle than dark matter. About dark energy, the problem is we know so little about dark energy that there are not even speculations on how we might relate it to something that we observe at the LHC. For dark matter, there is at least a lot of theoretical ideas on how it could relate something to a phenomenon we observe at colliders. For dark energy, that's less so.
We don't know what question to ask of the LHC.
Related to dark energy,
that's
yeah,
kind of
exactly. Yes, exactly. So
it's much weaker coupled than gravity. Right. Therefore, you wouldn't see that in the acceleration.
Right.
So
but I mean, it's important to know.
It is very possible that if we see something completely unexpected, maybe then that would relate to dark energy. Who knows? But there is no. Yeah, that's a good point. Thank you. Okay, so one of the big issues is the Higgs mechanism. So the Higgs boson was proposed in 1964, and it's a new scalar field which has a non-zero vacuum expectation value. You can see here a value of 246 GeV. This is the potential. And due to this Higgs field, so this Higgs field break with the non-zero value, it breaks the electroweak symmetry and generates 3 Goldstone bosons. These are the longitudinal components of the W and Z bosons, and 1 neutral Higgs boson. And this Higgs boson then also the masses of all fermions, so all fermions coupled to it, and their masses are proportional to this unknown Yukawa coupling, which is directly proportional to the mass. The other thing is dark matter. Here we know from galaxy rotation curves that there must be a big halo, a halo which contains dark matter. If there wasn't any dark matter, it would follow this dashed disk curve here, which is what characterizes the visible matter. But you see that the data clearly prefers a model where there is this halo. And there's other experiments, cosmic microwave background, for instance, that show this. And so what we know now is that the standard model only accounts for 20% of the matter of the universe, and there's many theorists that predict production of dark matter particles at the LHC. So this is an aerial picture here of the LHC in Geneva. This is here Lake Geneva. This is the Mont Blanc, the tallest mountain in Europe. Then the LHC has a circumference of 16.5 miles going through Switzerland and France. And there is protons going around one way and another way, so that we have then collisions occurring in these 4 yellow points, which is where the 4 experiments, 4 LHC experiments are: CMS, ATLAS, ALICE, and LHCb. So I'm myself a member of the ATLAS collaboration, and so are my colleagues from NYU, and I'll talk mostly about the physics that, well, only about the physics that ATLAS and CMS are doing right now. LHCb is a dedicated experiment probing CB violation, which might be related to the matter-antimatter asymmetry, and ALICE is probing with heavy ions, quark-gluon plasma. The energy that we've been running at most recently is 8 TeV. Each of the proton beams has a 4 TeV of energy. Here I have a little movie now that illustrates how we get these collisions. So here we have the protons being accelerated and pre-accelerators. Here the booster, the PS, the proton synchrotron. They're going to, this was at 25 GeV, then going to increasingly higher, larger accelerator, the SPS, 450 GeV. This is where the W and Z were discovered. And then going into the LHC ring. Here you see these blue, these are the big magnet structures. There was the standard model Lagrangian over there. And here is the border of Switzerland and France. And so now we're going into the tunnel. So we're now in the proton. These colorful things are quarks, the constituents of the protons. And now approaching the ATLAS experiment. So protons coming from the right, protons coming from the left, approaching each other. And then in the center of the ATLAS detector, we get this collision, and a spray of particles get produced. And we've surrounded the collision point with our detector so that we can measure every aspect of every single of these particles that get produced. OK, so the accelerator itself is an engineering marvel, in my opinion. So we have these dipole magnets. 8.4 Tesla dipole magnets. So we have protons, one set of protons going here, the other going that way around, and you see this complex magnetic field. And there's various big forces acting, of course, in these magnets. They are cooled to 1.9 Kelvin, and we have with over 90 tons of liquid helium. And the energy of the beam is very large. It's 360 megajoules. So this corresponds to the kinetic energy of a 15-ton truck going at 500 miles per hour. So it's very violent. So there is a very, as you probably know, we had a problem in 2008 when, in fact, we had a problem with the magnets because a resistance developed and that caused a 1-year shutdown of the LHC. So the safety of the machine to ensure that these big energies can be dumped safely if anything goes wrong is a big deal.
Can you explain what is 362 the energy of?
It's the kinetic energy of the beam. So
the beam. What collection of protons?
Okay. So this is approximately. So this is like 100 times 10 to the 9. So it's 10 to the 11 protons in a single bunch of protons.
This is times the number of bands.
And then there is exactly. And then there is 1,400 bunches we had now in the machine during run 1. So
that's the total that are going around.
That's the total, right.
And 362 is what?
So it's the total energy of all bunches together and all protons together. So the thing is, if, for instance, you had no protection and we just had a power glitch, this is the energy that would immediately go and destroy one of those, destroy one of those magnets.
Because every bunch would come by, so the kinetic energy of each bunch would somehow accumulate.
Yes.
When we dump the beam, we have to deal with that much energy
Right.
going
It's
around.
all the protons.
It's all the protons together. And this just shows a picture of the last magnet that was lowered here in 2007.
What about the stored magnetic energy from the magnets? Is it smaller or larger than the?
Oh, I don't know. It's also a lot. This is so when the incident happened. What happened was that the connectors between the magnets, a resistance developed. They warmed up. That then warmed up the helium, and then the helium. So the biggest issue was that because once the helium gets warmer than 1.9, then it goes from liquid to gas. And then, of course, it expands like crazy, and then a lot of force develops. So I don't know, actually, but I don't know what the forces are exactly that act in the magnet. I don't know if Andy or...
Multiply that by the volume of the tube and inject. Why don't you tell us that by the end of the talk?
Yeah, that's true, yeah. Okay. The ATLAS and CMS detectors that surround the interaction point are large multipurpose detectors, so they weigh about 10 kilotons, and ATLAS is 22 meters high, so it's about the height of a 4 or 5 story building. You see here 2 people standing on it, so you see the scale of the detector. They are both having an onion type structure, so many different technologies are encapsulating the interaction point to capture different kinds of particles. And this is here just to illustrate. So CMS is also extremely heavy. It weighs, in fact, more than the Eiffel Tower because its calorimeter is made out of lead. This is showing some pictures from the construction phase, how here a large part of the CMS detector gets lowered into the cavern. The whole detector is about 100 meters underground, which is where the LHC is. Here's several other pictures here of the cavern. If you haven't been to either ATLAS or CMS cavern, at the moment there is an opportunity because we're in a shutdown, so people can currently go and see the detector. So if you're interested, I can definitely help setting that up. But of course you have to come to CERN to do that. So this is here the concept of these detectors. So we try to identify all particles that are created in these collisions by having these different layers. So for instance, the inner tracking chamber measures the momenta of all charged particles because it's enclosed in a solenoidal field. And so because of the Lorentz force, we can then, from the deviation of from a straight line, we can work out what the momentum of the particle is, what the charge is, and of course the angles, etc. And then the calorimeters measure all the electron, photon, and hadron energies, and then the blue is the muon spectrometer, which is again a tracking chamber, and any particles that are visible in there are likely to be muons, or at least the chance that are not a muon are at the per mil level. This is just to show some of the tracking detectors. So the most inner detector that I've also worked on personally, so it's closest to my heart, is the pixel detector, silicon pixel detector, which consists of 80 million individual readout pixels It's the first detector that any particle will see, so we arrange them in concentric layers. So for instance, a particle gets produced here, and then it leaves hits in any of these concentric layers. The hit efficiencies of these particles, these detectors are typically greater than 99%. And then there is a lot of pattern recognition software we need in order to identify from these hits the trajectories of charged particles. Normally, so here I'm showing just one low momentum and one high momentum particle, but in a typical collision event, we have easily more than 100 particles at the same time, often 1,000 particles being produced. So then finding these patterns is quite challenging and in fact CPU intense. This is just showing you how global of an enterprise this is. ATLAS collaboration consists of 38 countries here and 3,000 scientists, and 1,000 of those scientists are actually students. And it was founded more than 20 years ago. This is just showing the age profile actually of our collaborators. So you see that indeed it's peaked here at low values. Nearly half the people are less than 35 years old. And here, for instance, you see some of the NYU students here in the ATLAS control room. The students are doing most of the work on the experiment. Okay, so then let's come to the data taking. So I wanted to briefly introduce luminosity. This is the single most important quantity for us that the collider delivers. So because it drives our ability to detect any new processes, the luminosity is given by the machine parameters. So one is the revolution frequency. The protons are going around 11,254 times each second. Another is the number of bunches, which is nearly 1,400 in run 1. Then it's the number of protons per bunch, which was about 1 times 10 to the 11, so 100. So that relates to your question of the energy, by the way. These were the numbers. And then the other thing is the width of the beam. So what it tells you is how many proton-proton collisions we get. The higher the current, the better, the higher the number of bunches, and you have to have them in a very small space in order to maximize the chance that they interact with each other. And then the rate of physics process is directly related to that. The number of observed events for any process is just given by this the integrated luminosity over time times the efficiency. And this is the task of the experimentalist, to maximize the efficiency given to build a detector that efficiently detects any processes, and then to develop cuts that detect those processes. And then there is the cross-section, which is really nature gives it to us, and then usually we have friendly theorists who are calculating that then for us. So see what we expect.
So the sigmas on top are?
It's the width of the beam.
Their lengths.
That's right. They are in microns.
Is an area.
Oh yes, sorry, yes. So these are right. Yes.
And that's how you get the dimensionless number. LD.
Right. So this is
frequency dt is
right. So the luminosity gets measured in exactly. The luminosity yes is measured exactly in inverse femtobarn or inverse centimeters squared, and this one is measured in barn. Yes. Exactly, and so it works out. Thank God. Okay. So the LHC has been delivering data to us in the past 3 years, 2010 through 2012, and you can see the tremendous progress here on this slide. So what this shows is this delivered luminosity in units of inverse femtobarn as a function of time. So you see that in 2010 we actually, you see it just as a flat line, but we got 0.05 inverse femtobarn, approximately 40 inverse picobarns. Then in 2011, still at the same energy, we got a data set much bigger, 100 times larger than what we had in 2010 already. And then in 2012, we got yet another increase of a factor of 4 in luminosity, plus we actually got an energy increase going from 70 eV to 80 eV. So that in total, we've integrated 28 inverse femtobarns. So this is actually, in just 3 years, this is twice the luminosity that was delivered at the Tevatron over a period of 10 years. So it's kind of like a factor of 6 better. The reason mostly is, well, one of the biggest reason is that the luminosity at the temperature was limited by the fact that it was using antiprotons, which are much harder to produce than protons and to collide. The peak instantaneous luminosity is 7.7 times 10 to the 33. The design of the LHC is slightly higher than that. It's 1 times 10 to the 34. Hasn't been reached yet. Will be reached during run 2. I'll talk to you about that later. This means that we're having 20 million collisions every second, 20 million events every second. We are only writing a small fraction of those to disk, only the 400 most interesting ones. This is one of the big challenges, actually, to figure out which are the 400 most interesting. And one of the big signatures that are, so we're looking for events which have either high momentum leptons or high momentum jets from quarks or large missing transverse energy, which I'll talk about a little more later. This is where I know NYU has been playing a big role in ensuring that we understand how to trigger, how to select the events with high missing transverse energy.
Events means collisions.
Well, so there's two things. Okay, let me come to that. So this is really events, but in every event, we actually have like 20 collisions. So, this is yeah, exactly. I'm coming to that in a moment. This data volume is also huge. It's 4 billion events every year. And every event is about 1.5 megabyte large.
Sorry.
Yes?
The fact that you had an improvement of factor of 4, for example, between
yes.
2011 and 2012.
Yes.
Was it even due to software improvement, or you actually had to do some work on the machine?
So it's work on the machine. It is primarily due to that they increased the number of protons per bunch. And they also decreased the width of the beams.
You didn't have any shutdown in the beginning?
We did have a shutdown, but it was only like a 2 or 3 months shutdown, and there isn't really that much you can do. I mean, it's.
There was some work. Anyway.
There was some work. I mean, there was some work by the machine, but it's not hardware work. It's more understanding how to optimize the machine to deliver higher currents without compromising the safety of the machine. The big issue here is to make sure that we can, you know, the higher the luminosity, the more dangerous it is, so so the safety needs to be ensured. So the price for high luminosity is pileup, which means exactly that we don't have only one collision per event, but we have actually many collisions per event. This just shows you, again, as a function of time, the number of collisions, number of proton-proton interactions per crossing or per event. And so you see that in the beginning it was about 1, and then it went up to 3 in 2010, while in 2012 it went up to values of 30 or so.
You can tell us what an event is.
Well, so an event, this is an event. Okay, so an event is a proton-proton collision which happens in a time window that we read out. Maybe that's a good. It's a snapshot. It's yeah, right. When there is a proton-proton crossing, we decide this looks interesting. We read it out. We write it to tape. But then it happens. So in this case, for instance, this is a candidate event for a Z to mu mu decay. So this is why we would have triggered this event, because it has 2 high momentum muons. However, as you see, there's all these. So this is actually showing the event vertices along the longitudinal direction. So protons are coming in from both sides. And one proton-proton collision produced a Z event. But then there's all these other dots here, where there's many charged particles. These are all charged particles coming from them, or charged particle candidates. And all of these are additional proton-proton collisions that happen at the same time, within the same 25 nanosecond window.
So an event is defined by your resolution, your temporal resolution.
That's how I would yes.
Yes, and what is 20 in answer?
So to collisions, this is the number of, so this is the number of collisions that happen during one event.
And they're kind of considered parasitic.
They're parasitic, that's right. So this is actually, it gives an experimental challenge because they are putting all kinds of stuff into our detector, which is unrelated to the hard scattering event we're really interested in. And this is actually already, we have the values beyond design, and we've had to develop many experimental techniques to ensure we can cope with this and can kind of subtract this parasitic collisions as a. Okay, one of the challenges is actually also CPU, that it takes a lot of computing to be able to read all these data, well, to store all these data. We have a total data volume of about 80 petabytes, which contains both the LHC data, but also Monte Carlo simulation data. We have very accurate simulations that tell us exactly what we predict, and they are completely instrumental to all our physics results, that we have these detailed Monte Carlo simulations, not only of the theoretical process, but also how these particles then interact in our detector, etc. It's a huge, it's critical to our work, and of course user data. And just to give you an idea, so to just reconstruct a single LHC event, if we're lucky, it takes only 15 seconds. But to simulate an event takes like 5 minutes, for instance. And Andy and his students have contributed a lot to the simulation here. And the data analysis is then done worldwide in more than 100 computing centers. So this shows, so there's 11 tier 1 centers in different countries. So the one here is in Brookhaven in the US, but then there's in England and Germany, etc. And then also more than 100 tier 2 centers worldwide. Okay, so let's come then to the physics results from run 1. So in general, the physics, the rate of processes that occurs depends on the mass of the particle. So if you imagine the collision here, the two protons interact via quarks or gluons inside the protons interact with each other, and they carry a momentum fraction of the proton x Bjorken, and then they produce some particle with a mass x. So then we can, the rate is then given here for different masses compared to the tevatron. So for instance, for producing a W boson via QQ bar production, which is about 80 GeV, the rate compared to the tevatron at this higher energy was about a factor of 3, which is not that impressive. However, for high mass particles like a Z prime, which is like a Z boson but at higher mass, at 1 TeV, it would be like 50. For gluinos, could have been 1,000, etc. So it's very.
What does SM mean? Z prime?
Oh, this means that it has standard model couplings, which is unlikely to be the case, but it's just as a benchmark. So depending on whether the process is mediated by gluons or by quarks, there's very large factors compared to the tevatron. So it was already clear earlier that even with only 1 inverse femtobarn of LHC data, the LHC would be competitive with 10 inverse femtobarn with the full tevatron data set. So it was very exciting. This then shows here visually how these cross-sections rise with energy for a variety of processes. So you see here W bosons, for instance, and here you see the rate at which they occur at the LHC. So we're producing at peak luminosity approximately 1,000 W bosons per second, producing 1 top quark per second, and we're producing 0.1 Higgs bosons per second. So this is one of the biggest problems actually already for, from the experimental analysis point of view. The Higgs actually, for instance, the Higgs in its diphoton decay mode, which is was the single most important one for the Higgs boson discovery, there's only 2 × 10⁻⁴ of those produced, while there is 10⁹ of any interaction. And then so all of these constitute backgrounds potentially to the more rare processes that we are interested in. So this is again, both the trigger is important, that we actually only write, remember we're only writing 400 per second, so we are not even able to write every W boson that we're getting. So we have to be very good about selecting the interesting events. Okay, but the first thing is also, in order to trust that we can actually observe some new physics, so the Higgs boson down here, we need to first make sure that we understand in our measurements, we measure measure the processes with large cross-sections. And the largest cross-section is by definition the total cross-section, which is just the cross-section that two protons go to anything. Two protons interact with each other and go to anything. And this is shown here. So this is the cross-section as a function of center of mass energies. This shows here measurements from the 60s. This was a very a very hot topic in the 60s, of course, to measure this. Now you see here there's a small rise, approximately logarithmic rise with energy. These are here the LHC measurements. No, sorry, here the LHC measurements. Here the tevatron measurements. And then there's also this actually is of relevance for Auger, for instance, so for cosmic ray experiments. Anyway, so you see that these models of these, and it is also important since we have, these are basically these parasitic collisions that overlay every single one. It is actually important that we have an idea of how they occur and that we can model these rates well. Then already with the 2010 data, we were able to see all kinds of other particles that were discovered in the 60s, 70s, and 80s, like the J psi, the upsilon, and the Z boson. And we've measured, of course, all their rates and understood whether they occur at the rates and with the properties as we expect them in the standard model. The Z boson in particular, I want to just illustrate a little bit of the experimental work is used within the experiments for understanding the detector in great detail. So in its lepton decay, we know the Z mass very well from experiments carried out at LEP and at SLD, and we also know we know what resolution we expect. So we can use this to constrain what the momentum and energy scales of our tracking detector for muons and of our electromagnetic calorimeter for electrons are. And you can see here an example where we have done different alignments. Basically, the summer 2011 has a smaller resolution than the spring 2011 because we have improved it by doing a better alignment. And we can also measure efficiencies. One thing that I'm showing you here is the relative energy scale for electrons. So this shows the stability in the energy response for the electromagnetic calorimeter. And you see, as a function of day in 2012, and you see how we are able to keep this stable at the level of less than 0.1%. This is very important for the Higgs boson search, as you'll see later. And this is to give you an idea how comprehensive of a measurement program we've had in Run 1. So without looking at all the details, you just see here, this is a number of physics processes going from W and Z production to top quark production, production of dye bosons, production, many, many processes. And in all cases, the gray shows the theory and the blue shows 7 TeV data and orange shows 8 TeV data. We don't have measurements yet in all cases for 8 TeV data, but you can see that whenever we have measurements, there is excellent agreement between the data and the theory in all cases. Okay, so then let me come to the Higgs boson search. I have a very brief excursion into history here. So the first paper that talked about how we can what the Higgs boson would phenomenologically look like was written in 1975 by John Ellis, Mary K. Gaillard, and Nanopoulos. So this was about 11 years after the Higgs boson paper by Peter Higgs and at the same time by Braut and Engler came out. And it has an interesting conclusion. It says we should perhaps finish with an apology and a caution. We apologize to experimentalists for having no idea what is the mass of the Higgs boson, blah, blah, blah. For these reasons, we do not want to encourage big experimental searches for the Higgs boson. So that's what they concluded at the time. Now, of course, then a lot happened 10 years later. Well, the standard model was much more established during about the mid-70s, early 80s, and by the mid-80s, early 90s, it was considered the single most important particle to find, and the LHC was designed, etc. Just to show you, this is showing here the decay branching ratio that they were considering. This mass scale here is MeV, so if the Higgs boson, since it couples, it generally couples always to the heaviest particle it is kinematically allowed to decay to. So at low masses it can only go to electrons, for instance, and then their scale ran out at 100 GeV, so this is here 10 to the 3. So now we still need to understand this. So in order to understand how to find the Higgs boson, we need to understand its production. First of all, so the Higgs boson gets produced in a variety of processes, which are sketched here. The most important one is this one, the gluon-gluon fusion process, where two gluons interact with each other via a top quark, and then the Higgs gets produced here. That is this cross-section here, which has approximately 1 picobarn cross-section. So per inverse femtobarn, we would produce 1,000 Higgs bosons like this, or if we had 20 inverse, so there would have been 20,000 Higgs bosons produced that way at the LHC so far. And then there's other processes, for instance, sorry, no, it's this one here. Sorry, so it's 10 picobarns, it's this one. This one here is the so-called vector boson fusion process, which is subleading, and then there's also WH and ZH. So the single most important, sorry, is this blue one up here. And we know the production rate to approximately 10%. And then the Higgs boson does
don't you need to know mass?
Right, this is the masses here. So this is as a function of mass.
Oh, that's the mass of the Higgs.
Right, right, right. And again, this is so this now shows the Higgs boson decay branching ratio as a function of the mass. So the mass, as you will see later, the mass turns out to be 125 GeV, so this is the most relevant here, but it depends strongly on the mass. And at this mass, the dominant decay goes to BB bar, but the ones that were actually used for the discovery were primarily the diphoton, which has only a rate of 0.2%, it's down here. The ZZ, which has a rate of 2.6%, but we pay an extra price because we only look at our Z bosons decaying to leptons. Then, and the WW. And the tau by now has also been seen, as you will see. So we're a bit lucky in this spot that we actually have access to many decays. If the Higgs boson was 160 GeV, it would nearly always decay only to W bosons. So how do we then look for the Higgs boson? So one of the most promising processes is here, the gluon-gluon fusion to a Higgs and then decaying to 2 photons. And the diphoton mass, which corresponds to the Higgs mass. The background, we have background here though, which are very large, where you just get diphotons produced via diagrams like these, which do not involve the Higgs boson. However, they do not peak at a value of the mass of the Higgs boson. And so what we expect to see is some falling spectrum here in yellow from backgrounds like these, plus a peak, which comes from this. Of course, then in nature, this is simulation, and in nature it wouldn't be colored red. So it's harder to know whether it's there. But it's there, so this shows here the data. So this shows here from the ATLAS Higgs search, now with the full data set from 2011 and 2012. So in total, 25 inverse femtobarns. So this shows the falling distribution of diphoton events. And then you see here in the middle this slight enhancement, and this is the interpreted as the Higgs boson. Here you see the ratio, but the difference between the number of observed events and the background prediction or the background fit, and you see there it's more easily observable. Now there's other processes. So this was also not only seen by ATLAS but also by CMS, and this shows an example of another process that was seen at the same time, which is Higgs decaying to ZZ, and these Z's both decaying to leptons. So here you see that there is a much better signal to background ratio. Here we have a signal to background of less than 1 in 10. While here we have approximately 1 to 1. The background is here the blue, and here's the peak on top of that background. Yes?
Is the reason diphoton was so important because why did you look for this really rare process?
For this one?
No, you said that the Higgs and photon.
Ah, right.
Is it just because that was the easiest to control the background?
Yes, so there's two, right, exactly. What is really good about both of these processes is that they generate narrow peaks, of which we can understand the resolution also extremely well. And we know that the background, there is no way it would make a peak. So it's a very in principle, it's a very simple analysis because we just need a falling fit for a falling exponential plus a peak of which we know the width. So it's really very robust. So we don't need to actually understand in detail what is the background to it. We can be completely agnostic. We just know, it's smooth. Now for here already, we're not just doing that. Here we are using Monte Carlo simulation to predict to us what the background is. So there, in principle, this is more error prone in principle. However, we wouldn't have to do it because, again, we have a very narrow peak here. Now, other decay channels like BB bar, there the problem is that the resolution, which is the biggest one, 60%, there the problem is that the resolution is very, very poor, and the background is even higher than this one. Yeah.
Did you explain how you know the width?
So we know it actually mostly from Z decays. I don't think I explained, but so the photons are detected and measured in the electromagnetic calorimeter, and Z to E events also. So electrons and photons are experimentally very, very closely related. And so by studying in detail Z decays to electrons, we understand the width very well.
So there are no particle is essentially zero here.
So there are no parameters. You determined all those parameters
we
from other experiments.
Well, it's within the ATLAS experiment from other events.
That's what I'm saying.
Yes.
Other
what she's saying, that the width is actually an experimental resolution.
That's right. It's not the physical width.
Right. Because the Higgs, the natural width of the Higgs itself is completely negligible. It's like 6 MeV or something like this. I don't know. It's an order MeV, while the resolution is.
Your instrument.
That's right. That's right. And this is why, actually, I mentioned earlier that one thing that goes into it is actually that how well we understand the response of our calorimeter as a function of time. If this is all over the place, this contributes to us having a broader width. The broader the width, the less are we able to pick out the Higgs boson from the background.
Sorry, another thing.
Yes?
When the data came up, I mean, I was told that there was some kind of friction between the ATLAS and the CMS data, which was more than like 3 sigma, which looks very, very, uncomfortable, like more than 99%. I mean, maybe I'm wrong. I was just told this. I wanted to ask you.
Well, in the beginning, so I don't know what snapshot in time this was because there have been so at the moment, ATLAS sees a slightly larger yield of Higgs bosons compared to the theoretical expectation in nearly all decay modes. And CMS sees a slightly smaller one. So if you average the two, but they are usually consistent within 1.5 sigma or something.
It's 1.5 because,
I don't know the letter. Actually, maybe Karen knows this better. Yeah. Oh, the mass discrepancy, right. Yes, no, the mass discrepancy, well, okay, so the mass discrepancy, okay, so actually I wasn't going to go into that, but I'm more than happy to. So the mass discrepancy is actually these two channels, in fact, the gamma gamma and the ZZ, they allow us to make a precision measurement of the mass because just the peak value gives us the mass. So yes, so in ATLAS, unfortunately, and if there's only one particle, of course, these two should have the same mass, yeah. But there is a discrepancy. Is it really too? Well, I think it's no. Well, it's yes. So it's uncomfortably large. It's nearly 3 sigma between the diphoton and the ZZ decay. However, the average of the two. So in CMS there is no such discrepancy. They have an excellent agreement between the two channels. However, the average of the two ATLAS measurements also agrees extremely well with that of CMS, which to me indicates possibly that indeed it's a statistical fluctuation. Now, as experimentalists, of course, what we had to do, so the diphoton decay is primarily determined by how well we understand the electromagnetic calorimeter, while for lepton one is actually the best sensitivity comes from the case where both these decay via muons. And so it is really driven by how well we understand our tracking detector. Again, in both cases, we've studied this really to death using Z decays, also J psi to muon decays, and so on. And so we didn't find anything that would indicate that there is a problem. So we think that experimentally there is no problem, and at the moment we think it's just statistically it can happen. It can happen, and it's a few percent. It's a few percent probability.
It's also quite a bit. It went from like 3 sigma to 2.5. It's been steadily.
It's gotten better.
Just with data.
With more data, it just goes down.
So you hope basically that as time goes by, it will go back.
Or it won't. I mean,
yeah, we'll see.
Yeah, right.
That's the test. You're saying is that's the test. If it goes away, then you're fine. If it doesn't go away, you might make.
Right. I mean, this is now stuck with us in run 1. I think with run 2 data, we should just have a fresh look and see what happens. And yeah.
And the spin zero was determined from the.
I'll show you in a second. The spin zero, so this, right, this is exactly, I mean, this doesn't really tell us anything other than that there is a peak and there is some particle decaying to 2 photons at some mass value. And now, how do we find out that this is actually the Higgs boson?
So actually, quick question. So what is the background due to the photon-photon channel?
So it's events like these.
But not just you said you just don't have to know even the exact.
You don't have to know.
We do know what it is. But
yes.
The final statement is just representing that.
Yes.
I don't think it's really calculable today.
Right. So there's several. Right. Okay. So.
Yeah, there's the box diagram things. It has uncertainty that's too big to. It's a lot bigger than the fit.
That's right.
Fit,
yes.
But it's calculable and consistent with.
I mean you typically have 20% uncertainties or so on this background.
Other events which give 2 photons. I mean, why just that?
No, it's not just that. No. There's also glue going via a 4-quark loop to 2 photons. So there's certainly uncertainties of the order of 20%, and there is also you can also get photons from pi-0 decays. Yeah. And that we certainly never rely on calculations for that. That Pythia, which is the main Monte Carlo, overestimates that by a factor of 2 or something. So we don't, but we have studied in depth the background composition. We know, for instance, that here 80% of the background does actually come from genuine photons and not pi-0. It's only about 20% that comes from pi-0s. And we've studied it in depth also to motivate the functional form we're using. For that, we've used Monte Carlo and simulation to guess the functional form.
In the other process, of course, you took into account the fact that there can be some branch travel, so you don't see.
Yes.
You don't see the actual. You don't reconstruct the full mass of the Higgs by looking just at the charge.
Right. But that our simulation knows about that then also. So yes, right. Okay, so then the big question is this what we found actually the standard model Higgs boson? And indeed, what we're looking at is on one hand we are comparing the rate of what we see to that predicted by the standard model. So the rate in the standard model is predicted by the mass of these particles. And the coupling, which is directly related to the mass. So just the fact that they all agree with the standard model prediction already gives us an idea that it actually does couple to mass. So for instance, we see the Higgs to tau decay now with a significance of about 4 sigma, and it's consistent with the standard model prediction. We do not see Higgs to mu, which is unfortunately in this plot. So that already tells us, and these muon and tau are basically the same theoretically, apart from their different masses, so that already tells us, and the muon is actually much easier to detect. So if the muon and tau coupling were the same, we would see both of them, but we don't see the muon. So we're already, so these rates, the rates that they agree with the standard model indicates us that it's very similar to the, well, it is very consistent with the standard model Higgs particle. However, we are of course not testing this to any precision yet. This is only here at the moment our measurements have uncertainties of between 20 and 50%. So it's really still very early days. Another thing we're doing is to indeed understand what are its spin and parity, and for this we use angular distribution. This is showing just one of them again in the diphoton channel. So this shows the angle in the Collins-Soper frame or whatever. So it shows some angular variable, and you see here the red is for the 0 plus hypothesis, so spin 0 and positive parity, and the blue is for a graviton type particle which has a spin of 2. And
for which process is this?
So this is for glue going to X, going to gamma gamma. So and yeah, gamma gamma. Sorry, yes. There's also in the 4 lepton. This is just one example. So there's more. Anyway, so here the data are more consistent with the 0 plus than the 2 plus hypothesis. So we're ruling out any of these other hypotheses. And so this is actually also where a lot of people here have contributed to. Okay, so now that we have the Higgs boson, we have, however, a new problem, which is the hierarchy problem, which was already anticipated before the Higgs boson was found, but by finding it, it's kind of reinforced. And the thing is that the Higgs boson has a tree mass, just like any particles. There is a tree level mass, and then there are quantum corrections to that. And for the Higgs mass, they come from, for instance, the top loop, a loop due to the W and Z bosons, and the Higgs self energy itself. And the problem is that this is a very large correction. So this correction, even if we cut off new physics, so the correction it receives is of this scale. So if, and here lambda is the scale of new physics, so if we set that to the GATT scale, this is just a gigantic correction, and we need to fine-tune this tree mass to be exactly the opposite of that, to cancel it, to get to a number which is of the order of 100 GeV. And so this is a huge puzzle that the theorists have been worrying about since more than 20 years. And it can only be solved by new physics at the TV scale, and there's thousands of papers also by Neil and Josh, for instance, on this. And so how can this be solved? So the way to solve it, one way to solve it, and that's the mainstream way of solving, is to postulate supersymmetric particles. So instead of, so for each standard model particle, we have another particle which has a different spin. So for the electron, which is a spin 1/2 particle, we get a selectron which is spin 0. So now we get actually more spin 0 particles. It also means that the Higgs isn't the only spin 0 particle in nature, but we get many more. So for the top quark, we get the stop. So for the muon, we get the smuon, etc., etc. So there's a lot of these. And then we also, for the particles which are spin 1 particles, for instance, the gluon, we get a spin 1/2 partner, which is the gluino. And for the photon, we get the photino, etc., etc. And so what then happens is that these new supersymmetric particles also make corrections to the Higgs mass. And so here's the stop loop, and this pretty much cancels out the top loop. However, for that to be the case, the mass of the stop quark needs to be relatively similar to the top. It can't be 1,000 TeV or something, then it doesn't work. It needs to be it needs to be pretty much below about a TeV, so close enough, maybe not more than a factor of 5 higher than the top quark for this to work quite well. There's big arguments on how much tuning, this is a matter of taste of the theorists, how much tuning they think is fine, 1%, 10%, 5%, and I don't know either. Mostly, the lower the stop mass is, the prettier would this would supersymmetry look, and the more likely it might be true in nature. And so, and if it's below a TeV, the good news is also that we can find it at the LHC. There's more virtues of supersymmetry, for instance, that all the forces that within the standard model, the forces do not unify. I think my pointer doesn't work anymore, but I can do without. Or do you have a hardware pointer? Okay, I'll just continue. And it also provides a candidate for dark matter. So it's very interesting to look for it, and so we do, and now these diagrams are, I'm afraid they're even more complicated than the Higgs diagrams. They appear in diagrams like these. So for instance, here we have produced 2 gluinos, and each of these gluinos decays to, via squarks to quarks. And then in addition, there is this particle here, which is the lightest neutralino. It's the lightest gaugino, and this is the particle which is also an excellent candidate for dark matter in the universe. It could be approximately, it's a neutral particle that doesn't interact much with anything and has a mass of order 100 GeV or so. And so what we're looking for is jets. These quarks look experimentally, they hadronize and we get jets of particles, and we look for so-called missing ET. This is due to these missing particles, and so since the total transverse energy in the event must be conserved, anything that's missing we attribute to those particles. And then we take the sum of all the jet PTs, all these transverse quantities, and we look at that. And this shows here the data compared to background estimates, and then these dashed curves show how a possible signal would look like. And we don't see any. The data are perfectly consistent with the background-only hypothesis. And this lets us exclude, in this case, for instance, so this shows here the gluino mass on the x-axis and the LSP mass, the neutralino mass, on the y-axis. So anything below this red line here is excluded by these data. So what it shows is that for gluino masses up to about 1.4 TeV, we exclude this as long as this neutralino mass is below about 400 GeV. So this corner. If the neutralino mass is 600 GeV, we have nothing to say on this yet.
Sorry, what are the stars?
The stars are just benchmark models that were used to optimize the analysis. They don't have any real significance. Oh, thank you. Another search, I told you that the stop quark was particularly important for this hierarchy problem. So it may just be that all other SUSY particles we don't really see, but let's just see if the stop mass at least is there or below a TeV or so. So we're looking for that in events like this where we have stop quarks being produced, and they would decay to top quarks. And again, this lightest neutralino. So we're looking at the missing transverse energy in events which have 2 top quarks. And you see again these dashed lines would be a signal, but the data are consistent with the background hypothesis. And here we at the moment, so this is a rather complicated plot which indicates here we're doing many searches. We're really vigorously looking for this in all kinds of possible signatures. And we are able to exclude masses below about 600 GeV as long as the neutralino is below about 200 GeV. But there are many caveats here. But as you can see, we're not yet probing up to 1 TeV, and we're also only probing here masses below 200 GeV. So it could easily be 300 and 700 or something. We wouldn't have seen that yet. There's also many other searches which are relevant. For instance, one could look also for, one can give up on solving the hierarchy problem, but still want, for instance, dark matter candidates and unification. In this case, one could say, well, all the squawks, the stop now can be very heavy. I don't care, but I still want the gluino and the gauginos to be rather light. So in this, here one could have rather spectacular signatures that one would have metastable gluinos, which could have a lifetime bigger than a microsecond, and then they would much longer than the beam crossing spacing. And so then what happens is they get stuck in the calorimeter, and at some point in time, whenever they are pleased, they would decay and leave a big jet. This analysis was actually pioneered by Andy at D0 and now done here at ATLAS also. So this shows here the jet energy in such events, and here the main backgrounds to this are not collision events, but rather cosmic rays, muons from cosmic rays, which are very energetic and causing and interacting in the calorimeter, or also muons from beam halo. And you see that the data unfortunately agree with these backgrounds, and the signal would look here very spectacular in this quantity, but isn't observed. And so this again can be used to constrain such particles. So the gluino masses are here now, the gluino masses on the y-axis, so up to 800 is excluded. And this is the lifetime here. So this is a microsecond, and this is 10 to the 6 seconds. So over a large period, this is the order of a year. So if it has any of these lifetimes, we can also exclude this. Yes?
Sorry. So speed of light's 300 meters per microsecond?
A foot per nanosecond.
Yeah.
Yes.
Sorry.
Yes.
1,000 feet per microsecond.
Yes.
So why, after a microsecond, are they still around the sea? Like, if these are relativistic particles, right?
Yeah. So sorry. What's the question? So
like, don't they leave the detector in a microsecond?
Yeah, they interact and they get stuck in the material.
They get
so
stuck.
they're like scattering around.
Well, then they stop. And they sit there for a bit.
Right. Okay. Yeah, they sit there at basically 0 velocity, and then they decay. So actually, of course, then you can ask, well, if that happens when another event is occurring, how would I know, right? So the data that is being used for this is during a so-called, it's during a gap. There is a relatively long gap during LHC data. Yeah, which is approximately 20% of all bunches are unfilled. So they're looking in those. So then nothing should appear. And then if something appears, it must be from some either cosmics or related to the beam, but something that happened earlier. Okay, so I don't want to show you all searches in ATLAS. It would take me like days or weeks, I don't know. So this shows you a large number of other searches that we're doing. We're very vigorous in trying to look for new particles. This is supersymmetric particles. We also look for all kinds of other particles and haven't found any. So to summarize, run one, but is that first of all, I mean, the LHC machine and the detector worked very well, but the machine ran only at about half the energy of its design. We've published ATLAS and CMS together, have published more than 600 papers in the past 4 years. And we had one surprise, which is that we found a new particle. Although I asked Steven Weinberg, and he said he was excited but not surprised that we found it. But anyway, so it's the only fundamental scalar in nature, and it plays a critical role in the standard model. And certainly the community is very excited. There's already more than 2,500 citations of the observation paper. And the other surprise is that there's no other particles that have been found. No sign of supersymmetry or any other new physics yet. There is an intense dialogue going on between theorists and experimentalists, just to indicate. So our SUSY papers have also more than 1,000 citations, mostly because theorists are trying to understand why we're not seeing something, or what could there still be, etc. So we need to have more data, and this is the roadmap of the LHC for the future, or rather, so this shows here the run 1 data. We're currently in the so-called long shutdown 1, during which we are upgrading our detector, and the machine is being upgraded to go to nearly the full energy, to 13 TeV. After that, we expect to get a factor of 5 more data than we had previously. And this last thing here, mu, is the pileup. So that also comes with the price that we have more of these parasitic collisions. But we are confident that we're able to handle them now, given the run 1 experience. So we're OK with that. Then they will run for 3 years. Then we have another 2-year shutdown to further increase the luminosity and to improve the detectors to be more able to cope with higher luminosity. And then another 3 years, then we have another upgrade, and then we increase by another factor of 10 the luminosity. So in order to take advantage from all this luminosity, we need to upgrade the detectors in order to improve the trigger capabilities. It's even, as you look for more and more rare processes, you're more and more drowning in all the background from standard model processes, and so we need to be able to discriminate the desired signal events from the background as early as possible and very quickly. And the other is that with this data, some of the detectors will will just not work anymore because of bandwidth limitations, that there's just too high occupancy to get the data out. And they also partially will suffer from radiation damage, which makes them less efficient. So there's a big upgrade plan from both ATLAS and CMS, just to give you an idea. There's the new pixel and strip tracker, that's about 130 million right there. So there's a lot of work already ongoing, both for all these phases. So what we're currently working on is this phase 0, and there I'm very pleased to say that we're completely on schedule. Both the LHC is, like last I heard, was 3 days delay, but on a 2-year shutdown, that's I don't think that one can call that even delay. And also ATLAS and CMS are well on track to be ready for them. So what can we do then in run 2 with these data? So this shows now, again, the luminosity ratio. I showed this before for LHC versus the Tevatron. Now I'm showing it for LHC at 13 TeV compared to 8 TeV. And you see that for particles with masses of about 2 TeV, we have an increase of a factor of 10. So even 1 inverse femtobarn, or a few inverse femtobarn already, we will improve the sensitivity compared to what we learned in run 1 for such particles. And we actually expect 15 to 30 inverse femtobarn by the end of 2015. So this shows here for Higgs, the increase is not so big. It's about a factor of 2.5, apart from if it's associated with TT bar. There we get a factor of 5 increase. But then for gluinos with 2 TeV, we get an increase which is even bigger than a factor of 100. So one thing is now, so this is for searching for directly for new particles. But the other thing is to understand precisely whether this Higgs particle we found has the properties of the standard model. And indeed, if you look, this is a table which just shows how the rate of the Higgs to a given decay, the coupling to vector bosons, B quarks, or photons would be modified by new particles that have a mass of 1 TeV. So new particles, for instance, a top partner or other new particles. And you can see, without figuring out the exact details, you can see that these deviations aren't that large. It's not that we're expecting here changes by factors of 3 or 4. These are typically at the 10% level. So in order to probe new particles at the TeV scale via the Higgs precision measurements, we need to be able to measure them at the level of a few percent in order to probe these theories in earnest. And at the moment, I already showed you that plot, at the moment we're only probing them at the 20 to 50% level, so we haven't got any sensitivity at all to such particles. We really need 3% or so. And this, in the future, we will get this much higher precision. So this shows here a table of couplings from CMS with 3,000 inverse femtobarns. You can see we can measure this between, this is 2 to 5%, depending on how optimistic we are about the assumptions, also on how well we understand the theoretical calculations. But you see, pretty much to all these particles, we're able to measure it at better than 10%, in many cases 2 or 3%. And the other thing is that we will gain access to rare decay. So, for instance, the muon will have we will even be able to measure the coupling to muons at the level of 8%, which we have not measured at all yet. We also will extend significantly the discovery reach, for instance, for these stop quarks that I talked about earlier. So this color here is what I showed earlier, where we're excluding below about 600 GeV and 200 GeV. This corner here, with the upgrades, we will be able to go out to values of for the exclusion, go up to values of 1.2 and ultimately up to 1.5 TeV, or discovery potential up to about 1.2 TeV. And for gluinos even higher. Okay, so then let me conclude. So we found, so the LHC worked fantastically well after 20 years of design and construction. We did find a new particle. This is the iconic plot from the discovery, showing here the probability that this observation was just a statistical fluke, and this was well below 5 sigma. We're above 5 sigma, well below 10 to the minus 7. And this shows here our spokesperson at the time, Fabiola Giannotti, who, I don't know who congratulated whom. They congratulated each other, I think Peter Higgs and Fabiola Giannotti. So this is, and so at the moment this is fully consistent with the standard model Higgs boson. And there is no other new particles found yet. But this was just the beginning. The high energy running is now starting in 2015. It's fully on schedule to start spring next year. We will increase the luminosity by a factor of 15 compared to by 2021, and then another factor of 10 by 2035. And there's major detector upgrade programs underway, and that will allow us to probe Higgs couplings with a precision of 2 to 8%, and then stop quarks up to 1.5 TeV. Thank you.
Thank you for that very nice talk, Beate, and thanks for plugging stuff we know, so I appreciate that. So, questions? We have time for a few. Yeah,
we had a talk by Arkani Ahmed recently, and he was really enthusiastic about the idea of 100 TeV collider.
Right.
So when I asked him how much it cost, he told me, I don't know, but the Chinese
have the money. Right. Yes. So there is an activity. I mean, he's director of an activity in that area. I mean, I'm excited about that too. I mean, it's just, it will take a while until we get it. I mean, I would be very pleased if we get it, but I mean, of course, in any case, what would be the best really, I mean, if I personally would like that we find some new particles now at the LHC, that will also make it certainly easier to get money, I think. And if we find some new particles, then we have a huge experimental and theoretical program to work out what we found, to find all the particles. I mean, it's not just one, but maybe it could be many and so on, right? And then it's very much possible. I think the LHC data already are indicating, for instance, if supersymmetry is true, it is very unlikely, I personally think, that all supersymmetric particles are in reach at the LHC. I think that's already clear from the data that we would be super lucky if that was the case. So then indeed we would need a higher energy collider to see the full spectrum of those particles. So that would be then a very good motivation for such a collider, I think. But no, I mean, of course, it's good. It's just for a theorist, it's very important to think maybe already beyond the LHC. Well, as an experimentalist, I somehow have the task to at least make the most also out of the machine we've got. So.
Just out of curiosity, like neglecting the cost of labor for all of the scientists and everything, how much in like just raw material cost does it cost to run the thing for like 20 minutes is electricity-wise?
Oh, that's a good question.
You save like $100,000 if you turn it off for 20 minutes in the middle of the day.
Yeah, it could be. It's a good question. I mean, the CERN annual budget is £1 billion Swiss francs, which is like $1.2 billion. But then I don't know. I don't know. I mean, that's a good question. I'll find that out. I don't know.
Well, part of it is that I think the bulk of the energy cost is in cryogenics, and so it's not the beam itself, and you can't just heat it up. Yeah, so it's actually kind of funny because during the LEP time it was warm magnets, and so we used to run in the summer and not in the winter, because in Europe they heat their houses with electricity in the winter, while in the U.S. we air condition our houses in the summer.
Right.
But with that logic of why the electricity in the deal doesn't really work is obviously for the LHC, because the cryogenics are always going. So we still operate that way, but
yeah, no, I don't know. I should find out. It's a good question. I'd like to know, actually.
And Fermi Lab 20 years ago was $50 billion a year was the electricity bill. 50 million?
Well, what's the power consumption?
Okay, I don't know either. I should know. It comes from French nuclear power plants, that I know.
Other questions?
I have one. Are you worried about the startup? What's your take on the risk of the LHC having problems with making turn back?
No, at the moment I'm not worried. I mean, they've been, I don't know, I mean, during run one I developed enormous confidence into the machine, right? Because I mean, for 2 years, I was basically every day in these. We have then run meetings on a daily basis to understand any problems from the last day. And for a year, I was there in every single one of them in ATLAS. And many times, every day there is a problem. But then they always solve it. All the time there's problems, and they just get solved. So at the moment, I mean, I see a lot of talks. I mean, it all sounds good. In the end, what is critical is what we will see is now the powering tests, how that works. But I think they have now, yeah. So this means so that now the machine will be cooled down, started to cool down in the summer, and then powered to the full energy, which means which will let us know whether we really can go to 13 TeV. I have every confidence that they can, but let's see. The other thing, what we don't know, in order to achieve really the goals, what we want to have 25 nanosecond bunch spacing instead of 50 nanoseconds, and in order to minimize this pileup from these parasitic collisions, and that is a bit tricky, and to which extent they can do that and how much luminosity we then get, we don't know yet. I mean, I would think that they managed to probably get things under control.
The initial view will be 50 nanoseconds, right?
Yes, but only one. So at the moment, the plan is that we run for about 1 inverse femtobarn, which is approximately 1 month with 50 nanoseconds, so that they can understand the machine at the higher energy under the conditions they've operated in run 1. And then then we will go. So the issue is beam-beam interactions. The closer the bunches are together, and then there is a week of what they call scrubbing, which is minimizing those, and then they will go to the 25 nanoseconds. So that's at the moment the planning. But there is a big planning meeting in Chamonix end of September, and so that's when the plan will be confirmed at the moment. But normally, yeah.
Did you mention what LHCb and ALICE are?
I said what they ever, but only very, very briefly. So they're also very important experiments. So LHCb is primarily studying. I mean, they have so many beautiful results. They're primarily studying CP violation in the B sector. I mean, the one very important result they and CMS found. I mean, so new physics, rather than looking for it directly through the production of particles, as we do in ATLAS and CMS, mostly, they can also contribute indirectly to low energy phenomena like B quark decays, B meson decays. And so this is what LHCb is looking for. And have very many beautiful results that are, however, also at this moment all consistent with the standard model expectation. But they're probing in a complementary way new physics. Yes, that's heavy, right, exactly. And then ALICE, ATLAS and CMS are all studying heavy ions. So the most important result there has been the observation of jet quenching, that you have somehow a jet produced and then nothing balancing it on the other side. And it's interpreted that due to the plasma, the whole thing gets messed up somehow. I mean, so that you decorrelate the hard interaction from what you observe in the detector by this plasma being present. So, yeah, but I wasn't gonna talk about that so much. But I mean, the most interesting thing is actually we ran with lead first, and now we ran in 2013 with proton lead, and there's a. To understand, and so in proton lead we shouldn't have a plasma produced. So this is very helpful to really understand now what we see in lead, which of the phenomena. I mean, it's a very experimental driven field. I mean, it's actually quite a lot of fun. There's a lot of phenomena which are interesting and remain to be understood.
When ions are running, what do you do in ATLAS?
We take data.
You take data?
Yes, fully. I mean, we have a very dedicated.
The rate is even higher, right?
Well, the rate of events is not higher, but the rate of tracks in a given event can be very high for the very central collisions. No, we're not afraid. No, in fact, it's interesting because it tests our tracking much more vigorously than any proton-proton. So before we even had any pileup in the 2010 heavy ion run, of course we were all like nervous about it, but the specs we were saying that we should be able to do it, you know, and we were pleased though then to see that there was no problems with the detector whatsoever, and we're actually able to reconstruct them and make sense out of these.
Brian Cole gave a colloquium here last semester. Who runs the heavy ion program at ATLAS, and so you can go back and watch that video. It's a very good talk.
Right.
At one time, there was talk about very forward detectors at 400 meters.
Yes.
Were they installed? Or?
So no, but so at 400 meters, unfortunately, it doesn't actually work, but we will install detectors most likely at 210 meters. So at 400 meters, the problem is that the latency, so we can again work this out from the speed of light and the distance of 400 meters, it takes more than 25 nanoseconds to send a signal back to ATLAS, so it cannot contribute to the trigger. It's too late. So 200 just about works, and so the plan is to install these now during run 2. That's the plan.
So 2015
Well, so it'll not be ready for the start of 2015, I think, but it'll be during the run. But there is also, yeah. So
there's no chance that we're going to run at 14 TeV and run 2?
Well, it's not. So at the moment, neither the experiment consider 14 versus 13 to be a priority. So one thing is to actually just fix the issue with the magnet connectors, but the other is also that superconducting magnets, they need to be trained. And normally they're supposed to only need to be trained once, and then they should remember that they've been trained, and then they're good to go forever. However, with a third of the LHC magnets, they've somehow lost their training, so they need to be retrained. And training a magnet, it goes completely exponential with how high energy you want to go. So if we want to really go to 14 TeV, it'll take them much longer to train the magnets. And so it doesn't seem like the highest priority right now for 2015. That doesn't mean that for 2016, maybe that could be in the cards, you know.
Should we switch in our simulations from 14 TeV to 13 TeV?
Yeah, so far, right. Yeah, for the preparation, that's the plan at the moment. That we.
We do all simulations.
I know, right, exactly. No, so the data challenge. So at the moment, ATLAS is planning this big data challenge. And so for that, we've already set it back now to 13 TeV, or at least that's what I heard. I haven't checked personally, but it's supposed to be, yeah.
Okay, very good. So let's thank Beate again.